This is part 1 of a 3-part series on the Cayley-Purser encryption algorithm: history, asymmetry, and a brief word on matrices. This particular algorithm was developed by a phenomenally brilliant young lady named Sarah Flannery when she was just 16 years old, a little over 20 years ago in the late 90s. Flannery grew up in County Cork, Ireland, with her parents and 4 younger brothers. Her father, David Flannery, was a mathematician himself. In her book, In Code, A Mathematical Journey, Flannery attributes her particular penchant for mathematics to her father's constant posing of mathematical puzzles to her and her brothers during her childhood. In her teens, Flannery took on a brief internship at Baltimore Technologies, and there began to develop what she would end up calling the Cayley-Purser algorithm, named after mathematicians Arthur Cayley and John Purser. Flannery took her work to various competitions and won the 1999 ESAT Young Scientist exhibition and a spot at the Intel ISEF Engineering Fair representing Ireland, among various other accolades. Flannery ended up getting a whole lot of media attention for her work, with the world heralding her as a girl genius who revolutionized the face of public key cryptography. If you've seen my earlier videos, you know that the reason that RSA is so strong is because of its usage of really large semi-prime numbers, like RSA 2048, the 617-digit semi-prime number pictured here. It's extraordinarily time-consuming to factor large semi-prime numbers. The difficulty of this task is what creates the trapdoor one-way function in RSA encryption, what makes it to its very core a public key crypto system. It's trivially easy to compute the product of 2 prime numbers, but it's infinitely more of a long, drawn-out process to factor this resulting semi-prime product. The Cayley-Purser algorithm, like RSA, is a public key crypto system. Unlike RSA, which depends upon the time-consuming nature of factoring large semi-primes, Cayley-Purser instead depends upon the non-commutative nature of matrices. If you're at all familiar with the rudiments of linear algebra, you know that an m by n matrix is just a rectangular array of numbers, where m is the number of rows in the matrix and n is the number of columns. Matrices can look like this: a 3 by 4 matrix, since there are 3 rows and 4 columns. They can also look like this, a 2 by 4 matrix, since there are 2 rows and once more 4 columns. And matrices can even look like this, a 10 by 12 binary matrix, so named because all the elements in this matrix are either 0 or 1. Flannery's algorithm relies on the fact that if you have some matrix A and some matrix B, then in general, matrix A times matrix B does not equal matrix B times matrix A. This is due to the non-commutative nature of matrices, and will serve as the trapdoor one-way function in the Cayley-Purser algorithm, much as semi-prime factorization does in RSA. More on that in the next video. Though it was a great success at first, the Cayley-Purser algorithm has since been found to be flawed as a public key crypto system. Personally, I still think that the sheer ingenuity and simple brilliance of this algorithm is really laudable and worth talking about. So to learn a bit about the mechanics of key generation in the Cayley-Purser algorithm, please check out my next video. As always, thank you for listening.